Hi, I'm Charles Preston, and this is a lab demonstration for the Emanations Lab. This particular lab deals with audio used as a channel to transmit data from one laptop computer to another laptop computer that's sitting at some distance away. In this particular case, it's only several feet away, but the distance could be greater. And the lab will demonstrate a denial of service attack for this audio communications channel and mitigation of that attack using one means, dealing with signal to noise ratio that I will explain more as we continue. Computers communicating by audio seem pretty innocuous if they're in a secured environment, but don't forget that computers communicating by audio could form a mesh network similar to computers using a wireless LAN with the right software. In other words, audio could be transmitted to computer number 2, which could send it to computer number 3, which could send it to computer number 4 for a greater distance than you might expect. In addition, hallways sometimes perform ducting, and low-level audio can carry further than you might expect. I'd like to describe the physical setup first. There are 4 laptops involved in this demonstration and a window to each laptop. The laptops are being operated by remote control using VNC software. There are 2 Linux laptops and 2 Windows laptops. The Linux laptops are the ones I'm indicating with the cursor. There's this one, which has a window for software called FLDIGI at the top of the window, and this one is labeled the transmitting computer. A Linux laptop with software designed to communicate using sound or a modem, modulate, demodulate. The bottom window is a second laptop running the same software, and you'll notice that in this particular case it says no call sign set, but the top one is transmitting, the bottom one is receiving. Both of these laptops have active microphones and speakers, and their purpose is to send or receive a pattern of sound that can transmit digital information, in this case, text that I typed in the windows. On the right-hand side, I have a Windows computer using a test tone generator that can transmit a variety of tones settable for loudness and frequency and varying if necessary, and broadband noise, which we won't get to in this particular demonstration, but the next lab demo will cover wideband noise. The bottom window is the 4th laptop. It's a Windows laptop running software called Spectrum Lab, and we're using the Spectrum Analyzer and what's called a waterfall window. I'm going to turn a single tone on at a single frequency, and you can see how it works. If I turn on this tone, it's a single narrow tone set at 1000 hertz. That's a little more than an octave above middle A for musically inclined people. And it sits on the same frequency. It doesn't change from 1000 hertz as the seconds roll past. And the color is the intensity or loudness that's being transmitted. So I'd like to point out that this Windows computer, again, is several feet away from the others. Its only function is to monitor and show us what's going on in the audio frequency domain. It has an active microphone. It's not used in transmitting or otherwise involved. It's just a monitor of what's going on. If I change the the loudness of the tone that's being transmitted here, you can watch the intensity or the color change. The color indicates amplitude, and in the spectrum analyzer display above the waterfall, you can see that this little spike showing energy versus frequency, 600 hertz, 800 hertz, 1000 hertz, 1200 hertz, is getting bigger. It's now 10 times louder than it was to begin with. If I turn it up to minus 10 dB, that's relative to 0 dB as the maximum. You notice it changes intensity. It gets taller here, showing higher amplitude, and it gets brighter, or tending from red to orange to yellow, getting even brighter here. And I'm going to turn it back down to minus 30, and the intensity or loudness picked up by the monitor, the other computer separated from it on the bottom, will change again. As soon as I turn it off, this is taking place in real time, but remote control. As soon as I turn it off, it goes away in the waterfall display and the spectrum analyzer display above. If I turn it on, it immediately shows up again. The setup over here, I'm going to clear these windows. Each of these computers has a working microphone, and as they pick up little bits of sound, they may try to decode them as data that's being sent from one computer to another. In this particular case, if I turn transmit on, I'm using a mode called binary phase shift keying. And what that means is that there are two tones instead of one, and you'll see those on the monitor spectrum analyzer. There are two tones, and in order to send data, the tones switch from the higher tone to the lower tone and back again. So if I type into the green window, as I type in, and as this computer sends the information, it shows up in the upper yellow portion of the window. As it's received on the lower computer, it prints out in this window. So we can see that at minus 15, and again, this is relative to 0 dB. So in order to make it lower in loudness, it can become minus 10, minus 15, or even lower. And you can see its color on the display. If I changed it so that it was louder, the color would change on the right-hand display in the waterfall. So you can see here that there was apparently some modulation that took place. And I'd like to magnify that. And let's see. Let's zoom out. Zoom in. And you can see that the tones are further apart, and you can begin to see more of a pattern if I type here again and it's able to send it from machine to machine, and you can see the tones shifting in a complex pattern as the different characters, ASCII characters, are sent. If I turn the transmitter off, then those tones will go away. After they shift briefly to a single tone in the center, the tones will go away. So I'm able to transmit data. Incidentally, this particular mode or protocol does not use any error correction. So if there's interference, the message received on the bottom might be incorrect. There's no retransmission or forward error correction mechanism. But I can send things back and forth. I'm going to turn this on again. Make sure I can still transmit. Okay, it looks like I can still transmit. And I'm going to clear this so you can see what's being sent right now. But before I do that, I'm going to turn on an audio tone at relatively low level. Now, look at the relative intensity of these tones. The single audio tone right in the middle appears to be louder than the two tones that make up the transmitting audio. So it's possible that that single tone, even though it's not occupying much spectrum space, could jam the communications here. Well, I don't see any transmitted data showing up on the bottom. If I turn off the interference, let's make sure we can still do this. Yep, looks like the communications path is still working. If I turn this on and change the loudness at the transmitter, what I'm doing is improving the signal-to-noise ratio at the receiving computer, at the receiving microphone. So now you can see that the intensity of the signal being transmitted, the binary phase shift keying signal being transmitted here, is approaching the interfering signal. Let's see if I can send something now. Well, that worked pretty good. So one way to overcome this interference is to improve the signal-to-noise ratio by improving the transmitting power. The signal-to-noise ratio required for this transmission is not very high because it's a protocol designed to operate at fairly low signal-to-noise ratios. For something like a television signal that's being transmitted or a video signal, you might have to have 30 or 40 dB signal-to-noise ratio to get a usable picture. Here, we don't need very much. Let's suppose I crank up the interfering signal. It's now minus 20. It's looking brighter. I go back over here. So I think the lesson is, if you have an interfering signal and you can increase the signal-to-noise ratio by increasing the transmitter power, you increase the signal-to-noise ratio at the receiver, you can still transmit the message. If the interfering party, or accidental interference, whatever it is able to increase their power, they may be able to cut you off again. That's the end of this demo. Thank you.